Thanks for joining today. This is part 5 of the technician live stream that I recorded in 2020 with the Hearst Amateur Radio Club. I took those 3 longer live streams and broke them down into sections so that they're easier to watch and easier to rewatch for those of you going to get your technician license. This is part 5, in which we go over multi-mode radio excitement and running some interference protection. This is part of the W5YI technician training book. Check the link in the description below for a link to the book that follows along with this series and to the playlist that has all of these parts of the technician stream broken down. You can go back and watch the ones that you need to study for. Go get your license and have fun doing so. 73, thank you for watching, and good luck on your test.
All right, so we're going to start getting into a little bit more technical information. We're gonna look inside some radios now and find out the basics. We're not going to go in depth. I'm not going to scare you off. We're going to go into the a high level, looking down at the pieces of a radio and how they essentially work. So we'll move on here. Let's go. Okay, there are different kinds of radios out there. You've heard me talk about different modes. That's like AM, sideband, SSB, FM, CW, digital. All of these combined together they're different modes. The computer, the radio functions a little bit different to make this work. You're probably familiar with FM and AM. You have those in your car. That's just two of many. So a radio a modern radio that you can buy will typically be what's called a multi-mode radio. Now, this beast that's on the radio on the screen right now, that is it's got a lot of knobs, so it's going to be very expensive. But if you can see my mouse, there's different modes. There's lower sideband, upper sideband, Morse code, AM, FM, RTTY, and then packet. And then over here, there's more. So there are. And then the small mobile one right here will also do quite a bit of what that will do, but you have to have some external hardware in order to make that work. Where this big monster radio right here has it all built in, the small mobile one, you would have to have something additional to interface to the radio rather than it having it all built in automatically. So CW and single sideband, that's SSB, capabilities make the multi-mode radio ideal for weak signal work. Now, weak signal is exactly what it sounds like. It's basically the radio being able to function and pull that either voice or digital information out of what would be considered a very weak signal. So that's going to be a common feature as you start looking on, in the catalogs and things like that, trying to decide what it is that you want to buy as your first radio or as your first HF, down the road. You'll start seeing all these different modes that they can do. So this is an aerial photo looking down at Northeast Tarrant County. This is I'm right here in this area, some right here. This is going to be Bedford. There's DFW Airport, the very edge of it, so you can kind of get a sense of where we are. This is 820. This is 183. So that I tell you that basically just so you can kind of get a feel for where you are in comparison to this the next screens that we're going to be showing. So when you look at this is basically the same thing as this. You're looking down and you can see you can see the houses, you can see the trees, you can see the roads. Same thing with this. You can look and you can see the capacitors, you can see the resistors, you can see the little roads right there that the electrons. So that is going to be the equivalent. That is basically a simple radio transceiver right here, and that's one way to look at that. So this is the same thing as this, as far as looking down at everything. Then we're going to look at this is going to be a road map. So this has got the same information as that first map. You see all the roads, and you can see what makes everything there in a little bit more detail. That's what this is. This is a schematic. So a schematic shows you every single path, every single component, just like this does right here. You can see DFW up at the corner. You can see the roads, and you can see everything. That's how this is. It is a breakdown, a roadmap of that very same radio transceiver that we just saw. Then we also have a map like this. This is that same map, but it's showing the cities in a block form. Excuse me, in a block form. So there's Bedford, Colleyville, Hearst, North Richland Hills, so on and so on. Looking at that, now you can kind of piece together what each city is doing. And that's what this right here, this is called a block diagram. And this basically gives you an overview of what each individual piece of that transceiver does. So there's your power supply and your mixers and everything like that. That is the way this just basically shows you the components and how they work together. This is called a functional block diagram. This block diagram describes the operation of a transmitter receiver in its most simple functional forms. So that is how we can basically break down that. This is going to be a block form right here. So this is going to be a CW transmitter block diagram. Your oscillator is going to be the part of the radio that actually generates your radio frequency signal. It generates that oscillating sine wave, radio wave. That's what actually does it. That is your oscillator, which then gets passed to your driver and your power amplifier, and that's all controlled. The actual transmission is controlled by your telegraph key. But that oscillator generates that signal where all the other information or signal is kind of added on in order to get that CW transmission. This is going to be an AM transmitter. So you still have your oscillator there doing the same thing as it did in that last one. But then you have your modulator. Your modulator is going to take your speech, and it's gonna convert that your analog speech that you're talking into that microphone. It's going to convert that into the electrical signals, which the modulator will then pass to the oscillator in order to overlay that new electrical signal onto the carrier. Again, your carrier is your actual RF signal. Your modulator puts in this case, the voice electrical signals onto that, which then passes it on down to the driver and the power amplifier. So you want to keep in. What you need to know here is what the modulator does. It takes your speech, your analog speech, and converts it. The microphone converts it into electrical signals, which then that modulator puts it onto the RF signal itself. So that is what it does. And this is an AM transmitter, so it's going to be amplitude modulated. So the louder you speak, the larger that modulated signal is going to be that goes onto that oscillator, into the oscillator to be put on a RF carrier. That can be confusing. I hope that made sense. If not, we can talk about it in just a few minutes. Because, like I said, this is kind of the a little bit more technical area, but it's once you get that basic function, here's what the oscillator does, you can start piecing it together and understanding how a basic transmitter will work. So in a super heterodyne receiver, the mixer converts the incoming radio frequency signal to a lower intermediate frequency that can be handled easier by the following stages in the radio. So here comes your radio frequency signal A right there. It's going to come into the mixer. That's going to convert the radio signal from one frequency to another. Down here, you've got your variable local oscillator frequency. Then it's all going to come in and be mixed into converted into signal C right here. This is going to be your constant intermediate frequency. Then that's going to be passed to the next stage, next to the next stage, and the next stage. A super heterodyne receiver, a lot of people will say is really the best kind of receiver, and so we want to keep it signal. We want to keep it simple. So your radio frequency in, it is going to take that RF and the local oscillator. It's going to mix those together and spit out the constant intermediate frequency. That's what you need to know. All right. This is a single conversion super heterodyne. Such big words. Super heterodyne radio. This is going to be an AM or a sideband receiver. Your product detector. So what this is going to do, your radio is going to be listening to everything. I mean, anything. It will receive every single thing that's out there. So your radio has to kind of isolate what you are asking it to listen to. So it's going to come in through the mixer, the intermediate frequency amplifier, your product detector right there. That's going to kind of isolate everything that it's receiving and make it into something that you can understand. It's all going to be passed through, and the radio is going to be doing. It's going to be stripping out what you don't want to hear. It's going to be converting it into the actual audio. Then it's going to go into the audio amplifier and out to your speakers. So your product detector is your important piece right here. This is what's going to kind of get rid of all that stuff that you're not interested in and present you with something that you can actually use. Some super heterodyne receivers have multiple IF stages. This will make it more selective to receive signals. So your selectivity, like I said, your radio is going to be receiving everything. It doesn't matter what frequency is. The antenna will detect it, and it's going to come in the radio, and the radio has to do something with it in order for you to have usable information. So this is going to be where the selectivity of the radio comes. This is going to be where the radio it's gonna filter out all that stuff you don't want to hear, and the more selective a radio is, the finer that receiver can kind of whittle down and narrow down what it is that you're wanting to hear. It's the ability of a receiver to discriminate between multiple signals. So that's, as you can see here, that is going to be controlled by these little doodads right there. I can't make out exactly what those are. Eyes aren't getting any better, but so that is what the selectivity in a radio is. It's the ability to narrow down what it is that you want to hear and get rid of all the extra. Here is an FM radio. As you can tell, it's quite a bit more complicated here. The more parts that it goes through, because an FM signal is it's a very wide band signal, and it does not work like AM does. So you have the signal coming in. Eventually, it's got to be limited down, because you're going to have all this stuff coming in, and then the limiter will pass the information over to the discriminator to filter. This is basically does the same thing as in the AM radio. It's going to cut down what it is that you're trying to hear. The identifying characteristics in this is going to be your limiter and your frequency discriminator. So this is what's going to be important in the FM receiver. This is something that you're going to have to memorize. Is in FM receivers, you're going to have a limiter and you're going to have a frequency discriminator, because it may ask you, it may give you this diagram and say, what kind of receiver is this? Well, if you see a limiter and you see a frequency discriminator, you can know that it's an FM receiver. All right, so some interference causes. There are multiple different kinds of interference. There is an overload. Your receiver is just a fundamental overload. The signal that's coming in is so strong on the receiver that it basically causes the receiver to not be able to receive. It's just so powerful that in the radio, in ham radio, you will often hear this referred to as desensing, desensitizing, desense. So that's something that you will experience as a ham radio operator if you transmit too close to another radio on the same frequency. Harmonics as you're transmitting, a harmonic is just a natural multiple of the frequency. So if I'm transmitting on, let me just say 200 megahertz, there's going to be a harmonic at 400 megahertz. Now, how well your radio is able to filter that out, basically a better radio will be able to filter out that harmonic. But there will be some harmonics there, just because it's just a multiple. It's like a double and then another double. So it's going to exist. Most radios do a very good job of filtering that out. A spurious emission is an unwanted non-harmonic RF signal. If your radio is starting to have problems, and while you're using it, it just spits out garbage on other frequencies, and it's causing interference, and it's doing weird things. These are unwanted non-harmonic RF signals. They will cause interference, and they can cause it because it's basically your radio is starting to degrade. That's one way you can think about it. The more your radio degrades, say the older it gets, or if it's damaged, it can start giving out spurious emissions, and you have to stop transmitting if somebody says, hey, your radio is not functioning properly. So newer radios, I haven't experienced that. I've got some cheap radios that I have not been generous or not been gentle with. They don't get used anymore because they do produce spurious emissions. And then FM over deviation. What this is, I want you to think of over deviation as, say you have a cup. Let's see, you have a cup of water. You have the ability on most radios to adjust your microphone gain. So you can adjust the sensitivity to how much your microphone can actually hear. It's like turning the volume up, except your microphone is listening and amplifying, essentially. So you have a cup of water, and you pour water into it. You've turned the microphone gain up a little bit. You're about 50%. You can still use the radio. You might start getting some complaints saying your signal is loud. Well, you can pour more water into it. 75%. You still have a little bit more. Once you get to 100%, that's it. Your radio does not have the ability to amplify your microphone signal anymore. But you could probably turn it up, and the actual radio doesn't have it. Now you could keep turning your microphone gain up to what would be the equivalent of 125%. Your radio is only capable of 100%. So what happens if you keep filling up a water bottle? Eventually, it's going to spill over, and you're going to get splatter. And so when that happens, you have to turn your microphone gain down because it's just too high. The radio can't handle that much, so you have to turn it down. Otherwise, it will be the same as if your cup, it's just overflowing and water splattering all over the place. So this right here, this is a mechanical filter. This is similar to like the filter in your air conditioner. It filters actual particles. There are certain particles that it filters out, and some go through. So this is a mechanical filter. You might use this if there's something next to your radio that's causing a lot of problem or causing a lot of interference. You could try some sort of a mechanical furnace filter. Then you have, excuse me, you have electronic bandpass filters, which combines inductors and capacitors in order to basically filter out what it is that you don't want to hear. In this case, we have 3 frequencies right there. All 3 of them are they're interfering with each other. We have this bandpass filter right here that will allow this middle frequency to go through with no problem, and then it will use these inductors and capacitors to filter those out. So multiple signals enter, and only the wanted will exit. You will oftentimes use those on HF in order to kind of filter out. If you have multiple transmitters operating at the same time, you can use a electronic bandpass filter to kind of isolate those multiple transmitters. They're heavily used on what we call field day, because you oftentimes have multiple transmitters that are very close to each other, and they can bleed over pretty bad. So this is something that you would use that for. A notch filter also uses inductors and capacitors, and what it does, multiple signals also will enter. This one is sometimes it's what it does is it does exactly the opposite of a bandpass filter. You have multiple signals coming in. Let's say you're on a radio and somebody's operating very close to you. You want to filter them out. You'll use a notch filter to filter out that center frequency right there, while the other 2 pass. So that is exactly the opposite of a bandpass, where bandpass allows, it filters everything but what you want, and then a notch filter will filter out what you don't want and allow everything else to pass. Notch filters are very common on HF radios because you can go in there and you can notch out a certain frequency. If somebody's talking on top of you, you can notch that out to where you do not hear them. They're still there, but you won't hear them because you have filtered them out, and then everything else around can continue to go through. So some of the received interference, radio antenna, high-low pass filter. Sometimes you can hear your voice in a regular radio. Same thing with a television. Not so much since digital has taken over. If you have a television and receiving an analog signal, and your neighbor says, "I hear all this noise every time you talk. I hear your voice in there." You would use a high or low pass filter to filter yourself out so it doesn't cause interference on their TV. Same thing with the radio. A telephone line, you'll use an RF filter. An RF filter was very common in the days of DSL. You always had to have that RF filter in there because you would get that interference on your telephone line. So these are some of the different kind of filters that you may encounter. Okay. In order to block out some of the radiated interference, like harmonics, you're going to use a low pass filter between the transmitters. So a low pass filter is going to allow the frequency that you want, and then it's going to basically block out I believe a low pass filter will block out higher frequencies in order to get rid of harmonics. Some of the interference that you may experience with your car is if you don't have a good ground, or your car doesn't have a very good ground, you might hear noise from your electrical system. Oftentimes it's a whine that will get higher and lower depending on the RPM of your car. You might hear it in your speaker. You might hear it on the transmitted signal. So what you would do for that was you get some sort of a filter. You can get ferrite beads or something along that lines. Make sure that your radio is grounded very thoroughly to a metal stud somewhere that does not it's not painted. That way it gets a good solid ground. So those are some of the different kinds. The most common is that whine. So I haven't really experienced a whine from most modern cars that I've driven, but the old ones where it was just everything was purely mechanical, it wasn't uncommon. So a little review. What could cause your FM signal to interfere with stations on nearby frequencies? It's going to be A, microphone gain too high, causing over deviation. Basically a splattering of your sound, and you can actually hear it, and it sounds like a splatter. It's just because too much gain is going into the radio and it can't handle it. What is the source of a high-pitched whine that varies with engine speed in a mobile transceiver's receiver audio? It's going to be the alternator. The faster the RPM, usually the higher the pitch the whine, and you can hear it as say somebody takes off from a stoplight. You can hear the whine go up and then back down, up and then back down, depending on the speed of the engine. What would cause a broadcast AM or FM radio to receive an amateur radio transmission unintentionally? It's going to be the receiver is unable to reject strong signals outside the AM or FM band. How can overload of a non-amateur radio or TV receiver by an amateur signal be reduced or eliminated? Going to be A, block the amateur signal with a filter at the antenna input of the receiver. That's if your transmission is causing interference on the TV, on your neighbor's TV. What is the name of a circuit that generates a signal of a desired frequency? That's the thing that actually makes the signal, the RF signal. It's going to be D. That's going to be your oscillator. That's going to be that thing that makes that oscillating, that up and down sine wave radio frequency. Which of the following is used to convert a radio signal from one frequency to another? That's going to be the mixer. Questions or anything? We are done with session 2. We can take some questions. We actually did very well on time tonight.